My name's Alex Rogers. I'm a Professor of Conservation Biology at the Department of Zoology, University of Oxford. I'm a marine biologist by training, and I wanted to be a marine biologist from the age of 12. For me, the fascination is with the animals and the ecosystems, and as I've worked over the years on the oceans, I've become more and more interested in human impacts on the oceans and how to manage our exploitation of marine ecosystems. And we're particularly interested in two types of ecosystem. This is one of them. This is a hydrothermal vent. And you can see here these characteristic chimneys which are formed from polymetallic sulfides. And this is one reason why these sites are now becoming of great interest to mining companies, because these things are sort of 10% or more of copper and also contain high concentrations of gold, silver, and other metals. Hydrothermal vents occur on mid-ocean ridges and in certain seamounts. They occur in settings where you have magma, molten rock basically, close to the surface of the seabed. And what happens is seawater sinks into the ocean's crust and it gets heated up and enriched in chemicals, including things like hydrogen sulfide and methane. And bacteria can use these chemicals as a source of energy. And that water becomes buoyant when it's heated. It comes rushing up and out of the seabed. And because bacteria can live off these chemicals, you get these really rich communities of animals living around the hydrothermal vents. And you'll see here this critter, if you like, walking around on the top of this chimney. And bear in mind, as I said, this water is at something like 350 degrees C, and you can see one of them just here. It's not actually in the water, but this animal actually getting very, very close. And this is them in close-up. This is in the southern site, and this is a new species of what's called yeti crabs. It says here density up to 600 per square metre. Actually, it was more like 2,000. And you'll see in a second just what I mean by high density of animals on the seabed. So you can see here they're in diffuse flow. This is at something like 20 degrees C. That's a lot of animals. We were beside ourselves on the ship when we saw this. It is simply one of the most incredible sights that's ever been seen around hydrothermal vent ecosystems throughout the history of their exploration. This is, as I said, it's a new species. It's not been described as yet. The males are considerably bigger than the females, and you can see them here basically scrapping for a position around the vents. Also, these systems are quite low in oxygen. They're very acidic, with the exception of a few vents which are at the opposite end. They have almost the pH of bleach. It's revolting stuff. It smells of rotten eggs, so it's really unpleasant. But hydrogen sulfide molecules actually block the uptake of oxygen by hemoglobin, and it also interferes with the electron transport chain, which is a fundamental part of our metabolism. So it's poisonous to humans and, in fact, most other multicellular animals through those routes. But hydrothermal vent animals have adapted to live in the presence of high concentrations of hydrogen sulfide. You've got the yeti crabs, but also these snails growing around the vent, and these snails have limpets on their backs here, And this animal is in fact another new species, a new genus of snail. This is called Gigantopelta. And again, they have bacteria in their tissues. So they're deriving nutrition from these bacteria, which in turn are oxidizing hydrogen sulfide from the vent waters. This is the process where microorganisms, in the case of the vents we're looking at, mainly oxidize hydrogen sulfide or methane to release energy. And that energy then drives the fixation of carbon, which is then converted to organic molecules or to energy for the organism to just burn up by the bacteria. It's been found that bacteria just in the normal deep water column actually undertake chemosynthesis using other chemicals. They oxidize ammonia, for example, to release energy. And these are particularly primitive types of microorganisms called archaea. So these really are hostile places for life. And what this has done for science is it's really extended the envelope that we now consider life can actually exist in. It was assumed that sunlight was a prerequisite for life because, of course, photosynthetic primary production is the basis of all the normal food webs that we usually experience. So on land, plants and trees use sunlight to power carbon fixation. They take up CO2. In the oceans, it's phytoplankton, microscopic algae and other organisms. But of course here, we've got an energy source which doesn't involve sunlight. And this really opened up the science of exobiology or astrobiology because it showed us that life could exist in conditions which we previously just didn't realise could support life. So here you can see one example, Europa, which is covered by ice, may well have hydrothermal activity lying deep beneath this liquid layer around this moon, and that may actually harbour life. I run a non-governmental organisation called IPSO, which is the International Programme on the State of the Ocean. And we've had a number of workshops with that NGO. And one of the main conclusions from one of those workshops was that one of the big problems we face is the communication of science to the public and to policymakers. For that reason, I take opportunities when I can to come and talk to people about our work and about the effects we're having even on the remotest parts of the ocean. Most of the animals that are found at hydrothermal vents are not found anywhere else. And these vents are almost like small islands where these animals exist. So obviously mining a hydrothermal vent site is very damaging. You just strip off all of the vent chimneys and the surrounding sediments. And at the moment, we have no idea what the effect of this is going to be. We think that for certain kinds of hydrothermal vents, they may be recolonized quite quickly from other nearby hydrothermal vents. But for other kinds, particularly those associated with slow spreading ridges, where the vents are much older, but you get far fewer over a given distance of ridge, those might be much more vulnerable and less resilient to this type of activity than from fast spreading ridges.